Hello dear students, welcome to the GDC classes in English. So today we are going to start with our topic of physical pharmacy, and here we will be covering all the important topics from the GPAT point of view. And as we know, the GPAT 2024 is approaching, so these topics will provide you a very good idea that from which topic questions can come, and we will be discussing some questions from previous years and like from the past 5 to 10 years of question papers. I have taken out some questions with their explanation so that we can get an idea of what is coming ahead and where which part the questions can come. Okay, so we will be covering from basic to the little advanced level, and the questions, the possibility, the probability of topics that can come in your exam, from which topic you need to cover, like for the physical pharmacy point of view only, right? So the topic that we are going to start today is the micromeritics. Okay, so I'll be writing the top definitions and important things right here only, and you all need to note it down all together and also understand the concepts which I will be discussing. Okay, so as the name suggests, micromeritics is the science and study of the small particles, right? Study of the small particles is termed as the micromeritics. So you all can write the science and technology. It is the science and technology which is related to smaller particles. Right? From the formulation point of view, we all now know that the particle size is a really important factor. Okay, so we all have to understand that how this particle size affects your basic release from the dosage forms, right, including the oral dosage forms, the injectables, the parenteral routes, the formulations that are given, the rectal route from which the formulations are given. All the designated routes and the types of formulation, their release is affected by the particle size. So we should know that which particle size, that the particle size should be small and controlled. That is how it offers the stability to the formulation. Okay, now we know that the uniformity of the particle, the stability of the particle, the powder packing, all this depends upon the particle size. All this depends upon the size of the particle. So by now you know, if the particle size is small, the surface area is large. The specific surface area is more. So the dissolution is better. And the absorption hence will also be better. Okay, so these concepts can be used for designing such a system with smaller size, which provides you with better stability, which provides you with better action, right, and a good formulation. Okay, so now we understand the smaller the particle size, the better the surface area, better the dissolution, and better will be the action. Okay, so the applications, from the applicability part, the particle size offers a lot of applications. The particle size reduction or the smaller particles offers a lot of applications. We'll discuss them in little brief. You should know that yes, this can be the application. We can also think like that also for the reduction of particle size. What can it offers to our advantage to our delivery systems, our formulations, right? So first is that I've already told is the dissolution, right? The smaller the particle size, the better will be the dissolution. Okay. Second is the appearance. I've already told you that if the particle size is bigger, there will be a difference in the texture, there will be difference in their appearance, their elegance, as well as that will affect your stability. I had mentioned the smaller the size of the particle, better will be its stability. Okay, so appearance is also linked to it. So you can write in the appearance that the particle size we know it is known to affect the texture, the taste of the formulation. Okay. Third is your flow ability. Another very important topic is the flow ability. Okay. Flow ability means what? Flow ability means the tendency of the particle to flow. Flow ability means what? The tendency of the particle to flow. Now, in case of powders, this is a very important topic from your exam point of view, which includes the powder flow properties. The powder flow properties. You have to keep in mind that as the particle size reduces, which imparts better flow properties. The particle size reduces, imparts the better flow properties. Okay, if the particle size is large, the flow properties will be poor. Okay, so that's how you can correlate the better, the smaller the size of the particle, the better will be its flow properties, right? So in case your particle is asymmetrical, in this case also what happens, the asymmetrical is the particle, so the poor will be its flow properties, and if the particles are symmetrical, the flow properties will be better. So if the particles are symmetrical, only the flow properties will then get better. In case of asymmetric particle, the flow properties will be poor, which indicates that in case of the powder packing also, only then the powder packing will be good in case your particles will be symmetrical. Okay, so the particle size small, symmetry between the particles, better will be their flow properties, right? In case of, now one more concept that you should know, it's very important, you can mark it as a star point. Asymmetrical particle. In case your particle is asymmetrical, you by now know that it will result into poor flow properties. Okay, so what can we do? We can improve these flow properties. Very important from the exam point of view. You should know there are certain glidants. Which can help you improve these flow properties. Directly question will be asked, out of the following, which among can be used to improve the powder flow properties? You should tick on the glidants without any doubt. Okay. So, except glidants, there are some granulation techniques also which can help you increase the powder flow properties, right? Just mention them. Asymmetrical particle will offer you the poor flow properties. Now, glidants can help you improve this powder flow properties, and the granulation techniques also can help you improve these powder flow properties. Okay, right? So, I hereby now include the three applications, including the resolution, the appearance, the flowability. Last is the weight uniformity. As now I have mentioned that the powder packing of symmetrically, if the particles will be symmetrical, you should know that if the powder particles are symmetrical, they provide good flow properties. If the powder particles are symmetrical, they provide good flow properties. Only then there will be good packing, right? Good packing between the particles that will offer, that means there is some sort of uniformity that exists between the particles. This will help them to be easily fed into the instrument. They will be compact, the packaging will be good, the particles will be symmetrically handled, there will be a uniformity. So we can indicate as a dose uniformity or the weight uniformity. Okay. from the exam point of view, the Gliadin point is the important topic, as well as the overview of these techniques is really important. Okay. Here I summarize the applications including the adsorption, the drug action, physical stability. I have already mentioned it that if the particle size is larger, there can be formation of agglomerates, right? The particles will agglomerate and they will get precipitate, which will cause instability. Okay, in case of larger particles. So the particle size will be smaller, the stability will be better. Similar is the case of the dose uniformity. For the particle size smaller will help you in good flow properties. The packing will be good. So there will be weight and dose uniformity, right? Similarly, the dissolution and the release. Obviously, if the particle size varies, there will be a major impact on the dissolution and the release of the release of the drug from its formulation. Okay. Next is the flowability. I have mentioned how these flow properties are so important for your powders. Okay. Coming to my next important point, that is the properties of powders. Now, properties of powders are classified into both fundamental and derived properties. Okay, fundamental properties and derived properties. Okay, the fundamental properties includes the particle size. Here it is mentioned: particle size distribution, particle shape, the surface area, the particle weight. All these belong to the individual, keeping in mind the individual particle, its size, shape, the volume that it occupies, the weight that it carries, and how this helps you to create a uniformity, the formulation with good parameters. Okay, so these all are important parameters. Then comes the derived properties, which includes the density, the porosity, the bulkiness, and the flow properties of powder, which are derived from the fundamental properties. These all are based upon the particles with the properties that are already available as fundamental properties. Okay. So next comes your very important topic. I would like to mention I would like to mention some points from the particle size and the size distribution, which are little important from your exam point of view. I would mention them here. Okay, so there are few things that you should keep in your mind before moving ahead. Particle size. Okay, now the particle size I have already mentioned and its size distribution are really important. Okay, now we generally assume that the particles are symmetrical, right? We assume that the particles are spherical in shape. Now these spherical particles, obviously they will have very important diameters with them, right? Suppose there is one spherical diameter, there is one volume diameter, there is one projected diameter. So all these particles, if we consider them into a sphere, have a certain diameter with them. Okay, from the exam point of view, as we are covering only the major topics, so you have to understand that apart from the diameters that I have mentioned, there are two other important diameter, which includes the ferrite diameter and Martin diameter, right? Your particles expressed in the form of diameters for their size, their surface area, and their distribution, right? So there are two other important, very important points that arise from this. You should know for the GPAT point of view. They are the most common topics from this very important topic from this exam point of view. I would always try to mention each and every topic that has already come or it is repeatedly coming in your exam. Okay, so you can mark it as a star component. Okay, now you have to understand, suppose this is a particle. Okay, suppose this is a particle. I will just give a brief of it, but you have to understand that how question arises. Okay. Now, this particle that we consider, this suppose is the projected diameter. This suppose we consider is the projected diameter of our particle. Okay, where will be the ferrite diameter and where will be the Martin diameter? We have to see that. Okay, the ferrite diameter will be actually this tangent that we have drawn. This is the ferrite diameter. Okay, and next is your Martin diameter, which is actually this portion. Okay, this is your Martin's diameter. Many a time this question has been asked. They have asked about the labeling. You will be given this diagram only of this particle. You will be asked to label the ferrite diameter and the Martin diameter. So there is a trick that you can write it down, is the FTMB. You should know this trick. FTMB means ferrite is related to the tangent, right? And Martin is related to the, which basically bisects your particle. This is basically the length which bisects your particle. You have already seen this is the length of the particle which actually bisects your particle, right? You can write it down in the ferrite diameter. You can write it is the mean distance. You can write in the ferrite diameter it is the mean distance between the two tangents on the opposite side. I have already mentioned the tangent. It is the mean distance. You can see this tangent. You can see this tangent. So the ferrite diameter will be mean distance. This mean distance from the tangents that are on opposite sides of the particles. Okay. So FT, it is a little easier to remember. FTMB. Okay. MB, Martin, it is the length that bisects the particle. You can already see this is the length that bisects the particle. Please, from the exam point of view, you cannot leave this topic. This is a really, really important topic. You can be given this particle that will be drawn and you might have to label them, that where is the ferrite's diameter and where is the Martin diameter. This will be labeled as A, this will be labeled as B. So you have to mention which among these the ferrite, which combination is correct, right? So you now know that the trick was FTMB, which means F is the ferrite's diameter, that actually is the tangent bit of a distance between the two tangents, and A is the Martin diameter, which is the line that bisects the particle. Okay, this is very important from your exam point of view. Okay, right. So let's move on to our next topic, which was the methods of particle size determination. Children, now from here also, students, this is a very important topic. Just by seeing what is drawn here, it can be deduced that this topic is very important. You know that the particle size offers a lot of advantages to your formulation and their parameters. So now the methods of the particle size determination are also that much important. Okay, so now we will enlist some important methods by which particle size can be estimated. Hereby, I would like you all to mention this as a very important star topic. From this chart only, there can be a lot of questions that can be asked. So keep in mind these four things. The optical microscopy is one method, the sieving is the other method, the sedimentation is the other method, and the conductivity is the other method. Okay, all these four methods along with the range that have been mentioned are very, very important from your exam point of view. Kindly note this thing down. Methods of particle size discrimination includes the optical microscopy, the sieving method, the sedimentation method, and the conductivity method. Very important. Few points that you should know I will include them in upcoming slides. Please mark it as very important. Okay. So the first that I have already, the image that I pasted here, you can see it is about the ferrets diameter and the Martin diameter. We have already mentioned in case of any asymmetrical particle, even if it is mentioned, you can here see that this is the ferret's diameter and here is the Martin's diameter, which actually bisects the particle. Okay, and ferret's diameter will be distance between the two tangents right above and below the particle. Okay, so other than this, first that method was the optical microscopy here, right? So from the optical microscopy only, you have one stage micropiece, right? A stage scale and the ocular scale that you have. Okay, from where you can deduce the actual, you get the numbers on the scale on your or placed on your microscope, where you can reduce the size which from which your particle is mentioned on the scale. How much scales you can count, and you can reduce the size, not reduce, I am saying deduce the size from the readings that are mentioned on the scale. Okay, now this method offers one little disadvantage, is that this method is little slow. Okay, you need to count each and every particle. This is a slightly slow method. Okay, next comes the sieving method. Now you know sieving method, as the name suggests, contains sieves, right? Sieves, you might know that sieves have little pores in them through which particles will be passed and they will be obtained. There will be some particles that will pass the sieve, and there will be some particles that will be left above the sieve. Okay, so they will be the so what we can do here is, in the sieving method, we place different sieves, as it is seen in this diagram also. We place different sieves each above each other. This is known as stacking of sieves above each other. Now you get the coarsest sieve above, and there are the set of sieves which go up to the finest level at the bottom, right? Above is the coarse sieve and below gets the finest. You get the finest size powders below and the coarse powders above. Okay, so as you know, this method is efficient. They are placed on a shaker. You can see they are placed on a shaker. This shaker now will move, and the sieves the sieve that are stacked upon each other, they will shake, and the particles will be come down and down and down, and they will be received in the pan. Okay, now you know there is a sieve shaker beneath them. You can collect the particles, right? And then what will happen? Now there will be one problem in this method. As I've mentioned in the optical microscopy part, there is that method we cannot make out about the depth of the particles, right? We cannot do the particle. The counting, in fact, is a very slow method. Okay, in this case, the sieves can get clogged. You know, here is the issue, that the sieves can get clogged, right? Or the agglomerates that will be formed, they will be very difficult to pass through these sieves. Okay, so this is a little disadvantage. We are covering these in brief because this here chart only that is present right in front of you is really important. You should know about the methods. I am telling you a little more where a question can arise. Just you should know the assembly, that the sieves are placed stacked each one upon another. Then there will be the coarsest sieve, the down you get is the finest sieve. They're placed on the shaker, and you get the appropriate size, right? Then comes up your sedimentation method. Okay. Now, in case of sedimentation method, you should know there is one Anderson pipette, which works based upon the sedimentation of particles. Okay, so this is here, you can see this is the Anderson pipette. This works based upon the sedimentation of the particles, right? You need not to go into the depth of it. You just need to memorize the apparatus and this very important equation below. This equation based upon the method of sedimentation is termed as the Stokes equation. Okay, here you can see the sedimentation size range is up from 1 to 200 micron. The method instrument is the Anderson pipette and the diameter will be the Stokes diameter. Okay, diameter is this. Okay, this is the volume, this is the diameter, and this is the your viscosity. This will be your viscosity. Okay, so if I deduce this equation into the Stokes equation as the Stokes diameter, the equation will be, I'll writing it here, 18 H delta S minus delta naught into GT. Okay, this HT, this H by T, this is the rate of sedimentation. This H by T is the rate of sedimentation. Okay, this delta S is the density of the particle. Density of the particle, and this is the density of the medium. Okay, so here I have summarized the techniques including the microscopy. You should memorize the size range. The instrument that has been used is the optical microscope. The diameters that we have talked about including the ferret's diameter, the Martin diameter and the projected one. Sieving, you have seen the sieve shaker that is placed over it, right? The sedimentation method is the Anderson pipette, which includes the Stokes equation and the Stokes diameter that I have mentioned here, right? Then comes your very important 5-star topic. I'll rate it as a 5-star topic, is the conductivity. You should memorize the size range and the instrument name and the volume diameter. Everything about it is really important. Once you start solving the questions, you will understand how important this slide right here, this table right here in front of you is really important and can answer a lot of questions from your exam point of view. Okay, so I'll be explaining a little about the conductivity. Okay, just wait for a second. From the conductivity point of view, you should know, there is an instrument known as Couldter-Counter. This method also is known as Couldter-Counter method. Very important, kindly mark it. It is a very important method, the Couldter-Counter method. Okay, this method is based upon the determination of particle volume. Very important. This line itself says very important. It helps you to determine the particle volume. Okay, from the size ranges as mentioned below, there comes its major principle, its basic principle. You should know its basic principle. Very important, please mark it. So the basic principle of the Couldter-Counter method includes that when a particle is suspended in a conducting liquid, when a particle is suspended in a conducting liquid and it passes through an orifice, there is a change in electrical resistance. There is a change in electrical resistance which will be directly proportional to the volume of particles. So it can be understood that each time the particle will pass, there will be a change in the electrical resistance as the particle passes through the orifice which is present inside these, that there will be some assembly which contains the conducting liquid, right? There will be an orifice there through which the particles will pass. Each time the particle passes through the orifice, there will be a change in the electrical resistance. This change in the electrical resistance is noted down and is considered to be directly proportional to the volume of particles. This method, I would like to mention one point of this method which makes it very different from other methods it includes the determination of particle volume that I've already told. Another thing is that it can measure a large number of particles at once. It can detect large number of particles. You should know about this thing, that because it is based upon the determination of electrical resistance, this can detect a large number of particles. Okay, they can help you count a large number of particles, including this 𝙂𝙂𝙎𝙬𝙎, that is HIEC has been mentioned. This instrument also works basis upon the conductivity or the Coulter-Counter method. This can determine up to 4,000 particles per second. Such an amazing thing. It can count up to 4,000 particles per second. Okay, very important from your exam point of view. I hope by now you understand that the particle size topic is really important and its determination. Okay, as the particle size is important, so is the determination of surface area is important. Okay, so we will see now few methods which help you determine the surface area of the particles. Here will we see some equations also. They are really important from your exam point of view. You should note them down and keep on memorizing them. Keep on learning the concept. You should do the revision every day. You should solve the questions every day. In the end of this video also, I'll be asking you some questions. You should be able to answer those. Okay. Now the surface area determination. We should know about the little basic concept about the surface area determination. Okay. So now you know that the particles are small, right? The particles are small. We have considered the aspects of reducing the particle size. Now the particle size, whenever the particle size is smaller, makes them a good absorbents for the absorption of gases. Okay, the smaller the particle size will make them good absorbents for the absorption of gases on their surface. Okay, so surface area determination will be based upon two things. One is the solute adsorption. Okay, other will be the gas adsorption. Very important from your exam point of view. You might now know the difference between the absorption and adsorption. Adsorption, AD, it is a surface phenomena, and absorption, it is the bulk phenomena, when something goes into the bulk and then gets absorbed. Adsorption is like absorbing upon the surface. These are some little basic concepts that you should know. So we can see that if in case of solute absorption, there is a suppose a particle. Okay, now you know this is the powder particle, right? Now there will be adsorption. I am making circles which will indicate the gas molecules, right? These gas molecules, these solute molecules, these not gas, solute molecules are adsorbed over the surface of your desired particle. So when you know this monolayer is formed above the surface of the particle, through which now the amount of the molecule adsorbed can be counted and the surface area can be determined. This is just the basic for the solute adsorption. Then comes your gas adsorption, which includes determination of gas that particles that had been adsorbed over your powder particles. The instrument that is used, very important from your exam point of view, is the quantassaw. Quantassaw. This is the equipment that is used for the adsorption of gas. By the name of gas adsorption, we know that on our particles there will be a certain gas that will be adsorbed over its surface. You should know the gas that is adsorbed is the nitrogen gas and the helium gas. Okay, as the gases are adsorbed on the surface, what will happen? There will create a difference in the, there will be a difference in the thermal conductivity. There will be a difference in the thermal conductivity. Sorry, as soon as they are adsorbed on the surface, there will be a thermal conductivity detector that will be able to detect these adsorption and forms a bell-shaped curve, right? From the curve that you get from the adsorption that has been done on the surface of your particles by this thermal conductivity detector, by the getting this curve, you can now assume that this will be the height, this will be the your area under the curve. From the parameters from the curve, that is the height, signal ratio, and the area under the curve, you can get the surface area, right? But there is one important equation that comes with it, is the BET equation. BET equation, very important. I'll repeat once again, very important from your exam point of view. BET equation. This BET equation will give you the volume of the gas that has been adsorbed over your powder particle at a particular pressure, right? That in 1 gram of the powder particle, how much gas is absorbed, how much volume of gas it absorbed at a particular pressure. This is given by the BET equation. So here I am writing the BET equation, again a 5-star topic. Okay, I have labeled it as a 5-star. So the equation is P upon P, P naught minus P is equals to 1 by VMB plus P minus 1 by P upon 1 B Vm upon me PP naught. Okay, this is a very important topic, very important equation, which is the BET equation, that gives you what you should write. It indicates, what does the BET equation indicates? It indicates the volume of gas absorbed by 1 gram of powder at a pressure P. Very, very important from your exam point of view. Okay, so this is your surface area determination method. There is one more surface area determination method. I hope by now you know the importance of BET equation, the adsorption of solute molecules, the adsorption of gas molecules. Okay, next comes up your another method for the determination of surface area. That is the air permeability method. First was the solute and gas adsorption method. Second is your air permeability method. Air permeability method. Okay, very important from your exam point of view. Now, air permeability method is based upon what? Like, if the powder, here we will take the powder particles that we require for the determination of surface area. They will be formed as a compacted mass. They will be formed into a compacted plug. Okay, then the surface area will be determined based upon the how much resistance it offers to the flow of air. Okay, so air permeability method, the basic principle includes when the, you should write, when the air is passed, when the air is passed through the powder sample that is compressed, to form plug or the compacted mass of the powder, the surface area of powder offers resistance to the flow of air, right? Very important. So this is explained by another important equation, that is derived from the Poiseuille equation, that is the 𝘂𝙎𝙎𝙎𝙬 equation. 𝘂𝙎𝙎𝙎𝙬 equation, very important. That equation was a 5-star point, the 𝘂𝙎𝙎𝙎𝙬 equation, and this air permeability method is also a 5-star point. You should memorize the equations very well from your GPAT point of view. Okay, so the equation is P is equals to A upon eta W square into delta PT upon KL into E square by 1 minus E square. Okay, this is your equation derived from the Poiseuille equation. As we can see here, V is the volume of air flowing. Okay, next is your D. D is your obviously internal diameter of the capillaries. Capillaries are nothing but where the powders are packed and the air is passed, airflow is maintained through them, and the surface area of the powder basically offers the resistance to this flow of air, and that is determined. Okay, D is the diameter, L indicates the length. Okay, delta P indicates the difference of pressure. Okay, K is the constant and E is the porosity. Another important point, porosity. Porosity is nothing but the measure of air spaces or voids between the particles. Okay, that you should know porosity. It is the difference, basically it measures the air spaces between the particles, or these are the voids between the particles. Okay, this yet again is another important method of surface area determination. Next comes your powder flow properties. Yet this is the derived property, as I've already shown you earlier. The derived properties are really important. Among these derived properties is the powder flow properties. We have seen, in case the particle is asymmetric, offers the poor powder flow properties. If the particle is symmetrical, it will offer good powder flow properties. Now, these powder flow properties can be estimated, can be evaluated using the below mentioned 3 parameters, including the compressibility index, the Hausner ratio, and the angle of repose. You can mention again as a 5-star topic, triple 5-star topic from your GPAT and other pharmacist exams also. This is the favorite topic that can come. Okay. So one by one we will be seeing this method of evaluation. First is your angle of repose. Now you should know by this method that there will be certain values that will be indicated from the derived properties, including if we will calculate the angle of repose, there will be certain value of the angle of repose, and by that value we can identify the nature. Okay, nature of the powder, right? If the nature of the powder flow, that it will be the excellent flow, that will be good flow, or that will be a bad flow, that will be passable or not, right? So first evaluation method is the angle of repose. Okay, angle of repose, please write it down. Angle of repose is defined as, please, I am writing it here, please note it down. angle of repose, it is defined as the angle between, it is defined as the angle between the free surface of the pile of powder and the horizontal plane. Okay, it is represented as tan theta is equals to h, which is the height of the pile, and r is the radius of the pile. Okay, now the theta will be what? It will be tan inverse h by r. This is your angle of repose. As shown in the image also, this is a hopper, this is a feed hopper from which the feed is coming down. Okay, from this hopper, the powder is flowing downwards and forms a heap of particle. This is a heap of particle. This is the, as mentioned, this is the height. You can measure it with the normal scale also, right? And then this is your radius. Okay, so this ratio indicating the height and the radius of the pile of your powder is the angle of repose. Right here is the table of the angle of repose, which indicates if the angle of repose is less than 25, the flow will be excellent. As the value of the angle of repose is increasing, right? If it's like 25 or 30, the flow will be good. If it's 30 to 40, the flow will be passable. If it will be greater than 40, it will be considered a very poor flow. By now, you might be clear with this topic. Okay, now I'll tell you how that question can arise. I'll write the question here. The question is, if the angle of repose is 50, please tick the nature of flow. It will be a good flow, it will be an excellent flow, it will be considered as a passable, or poor, or very poor, right? Now you can see the value is above 40. I have already mentioned if it's less than 25, the flow is excellent. If it's between 25 and 30, it is good. If it's 30 to 40, it's passable. If it's greater than 40, it's very poor. Obviously, 50 is greater than 40. So the option D is correct. Without any doubt, such questions are so easy to answer. Just by memorizing the table right here, you can answer this question very easily. Okay, you should just memorize the table. Second comes your Carr's index, right? Carr's index, also known as the compressibility index. This compressibility index, the formula for this compressibility index is the tap density. Very important from your exam point of view, minus bulk density upon tap density into 100, right? So before going into this, we should know what is the bulk density, what is the tap density, or in general what is density. We in our minor classes also, we have known that density is nothing but mass per unit volume, right? If the density is, if there is like you have just poured the powder as such, you have just poured the powder in your beaker, and the volume that it occupies is the bulk volume. But if you will tap it, and you will adjust the particles with this tapping device, there it will be the tapped volume, right? So just mass of the powders that you know upon the bulk volume, which is the volume that is the powder that is poured as such, which might have the gaps in between them, okay? Or it can be obtained by tapping, which will be the tapped volume, that will be the tap density. So this is the formula for compressibility: tap density minus bulk density upon tap density into 100. Very important from your exam point of view. Yet again, right in front of you is the range of the Carr's index, which indicates the nature of the property. If it's between 5 to 15, the property, this is excellent flow. If it is between 12 to 16, it will be a good flow. If it is between 18 to 21, it will be fair to passable. It is above, if it's from 22 to 35, it will be poor. If greater than like 35 or plus, it will be considered poor, or greater than 40, it will be considered very, 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 very poor, right? So this is an estimate range. You should know this table is highly important. Just like the angle of repose, if the question arises that the Carr's index, suppose the Carr's index value is near to 19, indicate the type of flow. Indicate the type of flow. You can see in the table itself, it lies from the fair to passable region, right, between the 18 to 21. Okay. Now we have discussed two methods for the evaluation of the powder flow properties, including the angle of repose, the compressibility index. Last one is the Hausner ratio. Okay. Hausner ratio, as you can see, the formula for the Hausner ratio is nothing but the tap density ratio of the tap density upon bulk density. You can see, just like the angle of repose with its value is indicated the type of flow, in the Carr's index also there is indicated the type of flow based upon the value of the Carr's index or the angle of repose. Similarly, here is the Hausner ratio, in which there are values between 1 to 1.1. The flow will be excellent. From 1.12 to 1.18, the flow will be good. From 1.19 to 1.125, the flow will be fair. 1.26 to 1.34, it will be passable. Above it will be poor, and more above more 1.46 will be very poor, and greater than 1.60 is very, very, very poor. Yet again, I am reminding you, these three tables are the 5-star tables. You can easily spot questions each time from this table only. Okay. Very important, very, very important from your exam point of view. You have to memorize them as such, right? This is very important, right? Again, I had already mentioned about this topic, that is the particle volume. Here is just, you can see the particle volume and how this particle volume is measured using the Coulter-Counter method. We have discussed it already, right? This was the fundamental property. Last that remains is your density. Density is yet again a derived property. Okay, we have mentioned, I have already told you about the true density, the bulk density. There is another, I have told you about the tap density. Okay, the true density, the granular density. I'll make another easy table for you. Here I will write the density. Here I'll write the name of the instrument. Here I'll write the formula also. Formula, the instrument and the density. Suppose first is your bulk density. Density in general, density means what? Mass upon volume. So here it will be mass upon VB. VB is what? Bulk volume, right? You have already known about the bulk volume. That suppose volume of powder that is as such poured into the any container or the beaker, which includes these voids, spaces, everything. That is your bulk volume. That can be measured by the bulk density apparatus. Bulk density apparatus. Okay. Next, corresponding to the granules is your granular density, which will be the ratio of mass of granules upon granular volume, right? The method of determination of granular volume will be mercury displacement method. Very important from exam point of view. Direct questions can be asked. Mercury displacement method. Okay. Third one is your true density, which is based upon the actual content of the right, which will be as the mass upon volume, that is the true volume, right? It is measured using helium pycnometer. Last one is your tap density. It is the mass upon tapped volume. Okay, you just have a mechanical tapping device for it that will remove all the spaces. Okay, mechanical tapping device. I hope this is clear to you all, right? These are the basic and some very, very important aspects from your exam point of view. I have tried to include all the topics that can come in your exam, or have already like in last 5 or 10 years they are on a repeat mode, right? So you can deduce that a lot of topics from this unit are really, really important from the physical pharmacy. Okay, now we will discuss some questions regarding it. So now you have an idea that we have talked about the derived property of powder and the fundamental properties of a powder. The question right in front of you, you should be able to answer me right now, okay? The following is not a derived property of powder. Includes the surface area, the particle size, the bulk density, or none of the above. Now I'll just give you 10 seconds to write down your answer and then we will discuss the answer. Okay students, now the answer is the C, bulk density, right? You might have seen the table that I have shown you in the start that includes the fundamental properties as particle size, size distribution, shape, surface area, volume and weight, and the derived property includes the density, right? It is mentioned there, density. So in here, the bulk density is not a derived property. A lot of you might have got this correct also because it was an easy question from the first slide only, okay? Next question. Following is not the method for determining the surface area of particles. Very important, I have mentioned it, right? There is the adsorption method, there is the mercury displacement method, there is the Bett equation method, and there is the air permeability method. The answer to this question will be which is not the method. We have already seen that the mercury displacement method is for the determination of what? For the determination of the granular density and not the surface area. We have seen the adsorption method. I have discussed about the solute adsorption, the gas adsorption. We have discussed about the Bett equation there. Okay, the air permeability method. We have discussed the 𝘾𝙀𝙎𝑎𝑟𝑒 equation there. All these were for the methods of determining the surface area. B, the mercury displacement method is the correct answer because the question has asked which is not the method. Okay. Next question. Following is related to the determination of air permeability method. You should know by now this question is a very easy question, right? Following is related to the air permeability method. We have discussed that for the determination of surface area, there are two methods including the solute adsorption, the gas adsorption method and the air permeability method, where we have mentioned the 𝘾𝙀𝙎𝑎𝑟𝑒 equation straight right away was the correct answer. This was in the adsorption part only. So answer that is correct is the A. Okay. I hope you all are getting it with me. You should be able to know the answers right away. We have discussed them. Okay. Yes, correct answer is A. Next, following is not used as a measure of flow property of powder. This question should be following is not used as a measure of for evaluation of flow property of powder. This question is very easy, very, very easy. We have seen there are three methods: the compressibility index, the Hausner ratio, and the angle of repose. We have just discussed. So students, you should be able to answer. The answer should be D, bulk density. Very correct answer. The question should be is very easy. It is right from your topic. It's very easy. You should not miss such important topics. Alright. Next, the instrument used for measuring the volume of particles. Here also, I should not even read the options because the answer is very clear in my head. I have mentioned there is only one instrument that is used for the method of determining volume of particles. In 10 seconds only, tick the correct answer and we'll be coming back to you. Okay, option A, hydrometer. Option B is the balance. Option C is the Anderson pipette. And option D is the Couldter-Counter method. You should just read the question and know the answer in your head, right? We already know that the fastest method is the Couldter-Counter method used for the determination of particle volume. Very important. We had discussed about the Couldter-Counter method. Right away the answer is D, Couldter-Counter method. We have already seen, right? Next, if the value of Carr's index of a powder is 10%, then what is the powder flow? We have seen this question. I'll give you 10 seconds to answer. So yes, if everybody has seen this table right in front of them, the values 5 to 10 indicates the excellent flow properties, right? So the answer will be, if it's like 10%, the answer will be excellent. Option B is the correct answer because the 10% obviously lies between the 5 to 15. Okay, this, right? Last question from the first topic that I have told. Out of the following ingredients, which improves the powder flow properties or the flow properties of the granules, including the glidants, the emollients, the lubricants and the surfactants. I hope you are able to answer this question. I had mentioned how much the topic powder flow property is important. So the correct answer you should be, I have told you about the two strategies that can be used for improving the powder flow properties. The correct answer out of the following glidant, emollient, lubricant and surfactants. The correct answer should be yes, A, glidant, right? Glidants are known to improve the powder flow properties, right? I hope you all had an amazing session. You all have enjoyed the topics. You all have got to learn new topics for your exam point of view, or you might have known about them. You might have got a good explanation regarding them. So thank you so much for this session, and I hope you all are able to answer the questions that I have mentioned here. These all are from your previous year exams, right? And thank you so much for this. Okay.